Hello there. We're at Chapter 2. We've finished Chapter 1, taking the test, and we're ready to find out more about derivatives and slopes of graphs. Here we go. We're going to be able to find tangent lines to a graph at a point, almost any graph at all, as long as it's continuous and differentiable. We're going to find the slopes of tangent lines to graphs, just approximately. It's not the best, but calculus is going to help us do better. We'll use the limit definition. The limits, remember, back in section 1.5, we're going to use that to find slopes. And we're going to use that to find derivatives of functions. And then we're going to talk about, very briefly, about the relationship between being differentiable and continuity of a function. So here we go, tangent line to a graph. You're familiar with tangents to circles, perhaps. This is a tangent line to any nice, I say nice, any curve that is a polynomial, for example, could have tangent lines. Now, the most important thing here is about the calculus, of course. Calculus, and we're talking about rates of changes of functions. Rates. That's the big deal here. So you find out how to find the slope of a line. It's the rate at which it rises or falls. Is it going up or going down? And basically you look at a curve or a line and you read it from left to right. Is it going up from left to right, or is it going down? The slope tells you that. If you don't have a line, then from one point to another, that slope might be different for the tangent. Here's an example right here. On the left-hand side, take this point right here, point number 1. Point number 1. Notice that the tangent here is going upward. Now you can't see it too well because it's so close to the curve, but the tangent would look something like this. It touches at that point, and we get as close as we can with the line to that without touching it if possible. Up a little bit further at point 2, it's not going quite as steep, but pretty steep, but it's different from the slope of the tangent at point 1. Up here at point 3, it's actually got a slope of 0 for that tangent line. Following that down here at the point 4, it's got a steep slope. In fact, it's very similar to the slope of the tangent line at point P2, but it's going down instead of up. Very important. Notice also, because this will become very important, as you travel along this line from left to right, notice that it goes from a positive slope because it's going up to 0 to negative, going down. Keep that in mind. This is also the high point where the slope is 0. Keep that in mind for later. Not immediately, but we'll get back there in time. So if you want to find out what the rate is at a single point, find the slope of the tangent line of that point. So here, for example, if we want to know how fast that function is increasing, just get the slope of the tangent line, and that tells you what it is. The tangent line is the one that best approximates the slope of the graph at that point. And we're going to be able to find those pretty easily. So back in geometry, you learned about tangent lines. And there's your tangent line right there. It's a line. It touches the circle with one point, P in this case, and it's got a particular slope. Now if you look at this line, the tangent line, you can see that from left to right it's going downward. So the slope on this tangent will be a negative something. If you were over here, the tangent would look like this, and the slope on this one, a different one, would be a positive something. Up here, of course, 0, because the tangent would be flat. Now, with a non-circular graph, non-circular, it actually might hit the graph at more than one point. Back here, notice, no matter where you draw the tangent, it's only going to hit at one place. But it could be, for a non-circular graph, it could hit at more than one place. For example, in this second graph, the one right here, notice if we extend this tangent to the left, it's going to hit at another point. That's possible. This is a different and more general form of tangency. We're going to see how you can take the limit and get a general tangent line, one that's good for any point on one of those graphs, whether it's here, or here, or here, or here. We're going to be able to find the slope of the tangent line anywhere at all. So you remember slope, rise over the run. Or slope equals the change in y over the change in x. You can also calculate it like this, subtracting the y coordinates on top, subtract the x coordinates on the bottom. If you've got 2 points, as we do here with 4, 5, and 2, 4, and we can use 0, 3 if we want to. Use any 2 of those at one time. Since this is a line, that slope is going to be the same regardless of whether we choose to use those 2 points or those 2 points, any combination at all. Since the tangent line approximates the slope at a point, we've got a problem. Because if we want the slope, notice back here, if we want the slope, we have to have 2 points. And if we want the slope at a point, we've got an issue. We can't use 1 point and get a slope. So what do? Well, one way to approximate the slope is take that point and then go over 1 unit and up somewhere close on that tangent line. Now this one gives us 1 to 2 or 2 to 1, y to 1. This isn't exactly what we'd want because we don't have 2 points. So what can we do? Well, this gives us the slope right here. Notice it rises 2 units for each unit change in x. This is key right here. Your slope talks about unit changes in x. Change the x by a positive 1. How does the y change? So looking at this graph over here, we can see the slope for that tangent line, change in y is 2, right there. Change in x is 1, and there's our slope. The slope, though, only for that particular point. If we picked a point up here, we'd have a different slope, because this curve that we've got, x squared, is not a line. So the slope is going to be different at different places. So since the tangent line has a slope of about 2, you can say the graph has a slope of about 2 at the point 1, 1. There's a picture of what we're going to do. So what we need is 2 points. So what we're going to do is we're going to say, okay, let's take this point and this point, since they're not too far apart, and we're going to find the slope of the line that touches those. Now, if that's not close enough to the slope, we could get a little bit closer like this and this. And that slope would be closer to the actual tangent line. So this is what we're working with. Remember, delta x is what we're calling h. There's h. H represents some small positive number. So we're going from this point to this point. As we go from the first point to the second point, our x value changes by just a little bit, h. So the change in x is h. As we do that, the function value, f value, is also going to change. The function value goes from f of x to f of x plus h, because it's not the same x anymore. We need those 2 points to be able to find the slope. Now notice that this is not going to give us the tangent line for that point, but it's an approximation. So what can we do? At that point of tangency, there's the second point. The first point is x f of x. Second point is x plus h, f of x plus h. If we draw the secant line, or the line that goes through those 2 points, we've got an approximation of the slope. And we can do it like this, with h's here, 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 here. Did I get them all? Oh, you can do that. So there's the formula for the slope. Make the switches from y's and x's to function notation, and you can get the slope of the secant line. The right side is called the difference quotient. I had us do that special one day because it is so important. This gives us slopes of secant lines. Now, here's the beauty of this whole thing. We want the slope of the tangent line for this point right here in the bottom left. We can't do it with 1 point, we have to have 2 points. So we pick another point up here, not too far away, because the farther away it is, the less likely it is to be close to the slope we really need. So make sure this isn't too big, the delta x or h in our case. Now what I can do to get a better approximation is make this value, the delta x or the h, make that smaller. That way this tangent line that we've got, or the secant line we've got, is closer to what the tangent line actually is going to be. There's your tangent line. The secant is a little bit off. Well, how can we make that better? Let's get those points closer. As it gets closer, it approaches the tangent line. Approaches. Doesn't that sound familiar? Like limits? As we approach that tangent line, we get so close that we know what the slope is. So here's the definition of the slope of a graph. Starting out with the slope of the secant, but as h approaches 0, this becomes close to the slope of the tangent line. Here's your basic formula. And all you need to do is take this f of x, fill in the difference quotient, and take the limit as h approaches 0. If the limit exists, of course. Next. Now, here's where we really get started. Find a formula for the slope of the graph of f of x equals x squared plus 1. What are the slopes at the points -1, 2 and 2, 5? We're going to find slopes for two different places. How do we start? First of all, we're going to write the slope of a secant line, alias the difference quotient. And we're using h's for these two. So what we've got here is, since this is x squared plus 1, here's the x, changed to an x plus h, and here's the h down here from the difference quotient. Here's the original function. You need to expand this term right here very carefully. X plus h, that's a binomial, square it, x squared plus 2xh plus h squared. Plus 1, and we're going to subtract the original. Here's what it looks like, and in your notes you might want to put h's here instead. Now what we've got is x squared and minus x squared cancel, gone. The plus 1 and the minus 1 cancel. This is what's left, 2xh plus h squared over h. Notice both those have h's, so we can factor out the h, and they cancel. What are we left with? 2x plus h. Now remember, we're taking the limit, so we're going to let h approach 0. Well, if h approaches 0, but not 0, but close to 0, what do we have left? The limit of that, as h approaches 0, the h is going to be essentially 0 as we get close enough. So the general slope, the slope anywhere on that curve, remember the curve was x squared plus 1, the slope anywhere on that is 2x. What does that mean? That means it depends on what point you actually pick. Put the x coordinate you're interested in from some point. We'll get to that in a second. Put that in where x is. Here's how it goes. For the specified points, first of all, this point, notice the x is at -1. So we put the -1 in for the x. Multiply that out. The slope here is a -2. For 2, 5, the x is 2 here. So we put 2 in for the x, and the slope there is a 4. Now, the derivative of a function. We're finally getting there. Notice there's a difference quotient staring at you. we're taking a limit, and we'll make those h's to make it a little bit simpler. That's your basic derivative. And notice that one notation we use is f prime of x. F of x is the original function. F prime of x is the derivative. Alias slope, alias some kind of rate. So in the example we just finished, we found that we started with this function, and we got another function that represents the derivative or the slope at this general point, any point on the curve. It's written or spoken as f prime of x, also known as the derivative of f at x. There's our definition. You got that? You need to know it because you'll have some kind of a test or quiz in not too long a fashion. Maybe a week from now, we'll have a quiz on just using that definition to get the derivative. That's how the derivative is defined. Of course, for us, we'll use h's here and here and here. Ready? Okay. There are other notations we use other than f prime of x. One is dy dx. I use that quite often. One reason I use it is the d stands for difference. If the y changes, or how much does the y change, it's sort of like delta y over delta x. If this changes by 1 unit, how much does that change at a particular point? So dy dx, you'll see me use often. Y prime also, that's the derivative of y. It's the same thing as this because y and f of x are exactly the same. There's another notation. This says take the derivative of. We put that in brackets just so we can highlight what the function is. And there's another one, and I frankly don't use this, but it is possible. It's the derivative of y with respect to x. But it's the same thing as the other three. These are the three I would be most likely to use. And you probably would find it the most helpful to use those. All right, let's get to a good example here. Find the derivative of y with respect to t. Well, one of the reasons for this being here is because we're not using x all the time. And this can be rather interesting. First of all, you're going to take the limit as h approaches 0 of what? Well, you know h is in the bottom. You know you're going to be subtracting because it's the difference quotient. And you're going to be subtracting 2 over t, the original function. And what's over here? Well, here we're going to have t plus h, where the t was, and of course 2 on the top. There's our difference quotient and our limit. Now this looks a little bit intriguing. It doesn't look like a lot of fun because of the fractions. However, let's take this 2 over t plus h, put it over here, and see if we can't work with that before we put it back in the difference quotient. If I'm going to subtract these, I need a common denominator. Now both of these are called prime expressions because you can't factor them. Since they're both prime expressions, the least common denominator is going to be the product of those two. You need this information. Now, if I'm going to do that, then I need to change both of these so they have the common denominator. That should sound familiar. Now, let's take this one right here, the 2 over t. How can I rewrite that so it has t plus h in the denominator? Well, if you take a look at this, what's missing in the denominator? I don't have a t plus h. So if I multiply the denominator by t plus h, I get the common denominator. Well, that's going to mess things up unless I also multiply by t plus h on the top. This is just the number 1. So if I multiply 2 over t by 1, I still have the same thing, but it'll look different. So what do I have now? 2 over t times t plus h over t plus h is 2t plus 2h. All right, so I can change this to 2t plus 2h. Now this has the common denominator. Now how about this one over here? I had 2 to begin with up here. What am I missing in the denominator? I'm missing a t. So I'll multiply top and bottom by t over t. So I'll have 2t over t times t plus h. Now I'm ready to actually subtract them. So what do I have over here? The limit as h approaches 0. In the numerator, I've got, notice I've got 2t over this and minus that over that. So in the numerator, there's my common denominator. And I'm going to subtract these. I've got 2t from the first fraction. And I'm subtracting this whole thing over here. So it'll be minus 2t minus 2h. And on the bottom, I still have h. All right. Now if you are following along, you've got the limit as h approaches 0. Notice on the top here, those first two terms give us 0. So what I have is minus 2h over t plus h. And since I'm dividing by h, I can multiply by 1 over h, and those h's will cancel. What's left? I've got the limit as h approaches 0 of, on the top, I've got a negative 2, that looks good. On the bottom, I've got t times t plus h. Now it's time to take the limit. As h approaches 0, this h effectively disappears. What's left? Well, the negative 2 is just negative 2. Here I've got t times only t. So this is t squared. There is the derivative. This is y prime. Starting with this, ending up with negative 2 over t squared. Now if you can do this, you're in great shape. If you can't, Get some practice. You need to get a little bit better at fractions, perhaps. Okay, we all did all those. Remember, those delta t's you can replace by h's. Notice here, that's where the t's gave us 0. Here is the 2h here. Here's the h here and the h here. A very fortunate dividing out. There's a simplified version before we take the limit. Now, direct substitution. Since we can put 0 in for h, we do it to get our limit. And there is our derivative. So we've got the derivative of y with respect to t. You've also practiced using something other than x. Last of all, but not least exactly, differentiability and continuity. A very quick summary on this, and then we'll breeze through the last slides. Let's call this D and this C just to make things real simple. If something is continuous, it might not be differentiable. For example, and we'll see an example, if you have something like this going on, it's continuous, but it's not differentiable there. However, if you have something that's differentiable, it automatically is continuous. So if we put this in terms of Venn diagram, maybe this would help a little bit. Here's my universal set of functions, and we've got a set of continuous functions in here. Some of those continuous functions are differentiable. So if it's differentiable, it's already continuous. If it's continuous, it might be differentiable and it might not. That's this section in a nutshell. Not every function is differentiable. Here are some pictures. Here's in the first one. It's definitely continuous. You can draw this curve without lifting your pencil. However, right here it's not differentiable. In the second one, it's not even continuous, so it's definitely not differentiable. In the third one, it's continuous. You wouldn't have to lift your pencil to draw that graph, but it's not differentiable right there. And the last one, it's continuous, but it's not differentiable right there. Each one is differentiable everywhere except there. If you look at those four that we talked about just seconds ago, everywhere else, if you stay away from x equals 0, it's differentiable. Here, here, as long as you stay away from x equals 0, you've got differentiability. Hope that gives you an idea. It's continuous everywhere, but not differentiable around x equals 0. So continuity is not strong enough to guarantee differentiability, but the converse is true. And there we go. we have finished the first section in chapter 2, and make sure you get plenty of practice because that quiz is likely coming up on finding a derivative using the limit definition is time consuming, and considering what you're going to know a couple weeks from now, it's really annoying because we're going to get some rules. So once we get past this, we're going to pick up some rules, and those rules will make us jump over the limit definition and get to some real derivatives without going through the limit definition. But for right now, you have to learn how to do the limit part because that's the foundation of everything. Well, that's it for now. I'll see you soon.